So I assume I'm audible, and you do see my my slides, right? So as it has just been told, sort of feel free to interrupt me whenever you want, whenever you can and want. So I'm not monitoring chat because there's no way, because I have just, well, I do have two screens, but everything shown just on one screen. So I'll every once in a while, sort of I'll pause and I'll stop and ask for questions, right? So it's great pleasure to being invited and to give a talk at Sharif University. So it was a little bit of a challenge to getting all of the approvals, but at last sort of I did it. I was able to get all the approvals. So the topic of my presentation, or my research here that I'm going to present today, is optimization and machine learning, and also AI, so deep learning. So it is on a technical side. So for those of you that are not that familiar with optimization, I'll try to keep it at a high level, but at certain points, I'm definitely going to go into details. And the talk is going to be quite mathematical. And as I said, as I kind of alluded, sort of I had to very quickly make a decision about a topic. That was almost a year ago. So, I at that time, sort of I picked this kind of a little bit more of a theoretical topic. So I am a full professor in the Department of Industrial Engineering and Management Sciences at Northwestern University. So Northwestern is in Chicago, Illinois. So besides being a full professor, I'm also the founding director of the Master of Science in Analytics, and I'm also director of the Center for Deep Learning at Northwestern University. All right, so first of all, I have to give full credit for this presentation and research work to Xin Quan. So he's a PhD candidate at Northwestern University. He is about to graduate and already works at Facebook in New York, or so he's wrapping up his thesis. And this work, the work that I'm presenting today, it's his next to the last chapter in his thesis. Right. So again, full acknowledgments to Xin. So he did all the research, and he also prepared the actual slides for this presentation. All right, so I'm not going to talk. So today I'm not going to talk about the Master of Science Analytics program. I'm not going to talk about the center either. So the focus is exclusively on the work that Xin has done. Right. So, okay. So a little bit of a background, and this is not background by myself, but background on, about the work. Right. So we study stochastic gradient descent. Right. So this is a very old algorithm. And in terms of in machine learning conjunction, sort of you have set of trainable parameters, W, all right? So, and you have a loss function, LW, and basically the problem is you want to minimize LW overall Ws, all right? So, and a special property in machine learning of the capital L function, loss function, is that you are given a set of samples, and L is essentially summation of Li's over all samples I. All right. So in other words, LW can be written as a summation with a bunch of terms, and the number of terms in the loss function is usually very big because it corresponds to the number of samples. All right. So we can easily talk about millions of samples. So LW has millions of summation terms. Right, so we also have, so the stochastic gradient also has learning rate alpha t. So the learning rate alpha t can vary with time. All right, so the algorithm essentially is you iteratively update your trainable parameters W, and you update them in the direction of the gradient. Right, so it's Wt plus 1 equals Wt minus learning rate or step size alpha t times the gradient. Right, so and I have already alluded that computing, so because the L term, the loss function, has a lot of summation terms, the gradient of summation is summation of the gradients. So you have to then, if you really want to calculate the exact gradient, you need to compute millions of gradients, right? So if you have 1 million samples, then computing the gradient means computing 1 million different gradients, one for each sample. And that can be very expensive, and it's just intractable in practice for realistic machine learning problems. So stochastic gradient circumvents this problem by randomly sampling a mini batch, which is denoted here as BT, mini batch of samples, and then calculating the gradient only over that mini batch of samples, and then averaging those gradients. Right. So in essence, we approximate the summation over 1 million terms. With a summation, typically it would be, let's say, 32 or 64 samples. All right. So in other words, the size of the mini batch typically say 32, 64, 16. All right. So you would approximate the summation of 1 million terms with a summation that has only 32 terms, and that implies that you only need to calculate 32 gradients instead of all 1 million gradients. All right, so and that makes the algorithm actually tractable. All right, so any questions at this point? None? All right, so moving on then. A nice property of stochastic gradient, or property, actually I should say requirement, is that when you sample your gradient, it should be an unbiased estimator, right? So which essentially means that the expectation of the sampled gradient should be the full gradient, right? So the left-hand side here is the expectation of the sampled gradient, right? So that's the given mini batch BT. So expectation is with respect to all mini batches BT. So you're randomly selecting mini batches. So in each iteration, you select a mini batch, you compute the mini batch gradient, and then you repeat. Select a different mini batch, randomly compute the gradient based on that mini batch, and you iterate this. Right? So what you need for this algorithm to make sense, for SGD to make sense, is you need your samples, your mini batches, you want them to be unbiased estimators. All right, so in this, the unbiased estimator property holds if your BTs are selected uniformly at random, right? So if you have 1 million samples, and in each iteration you select uniformly at random 32 samples, for example, so that gives you an unbiased estimator. All right, so the expectation here is with respect to all mini batches BT. All right, so this is a standard form of the stochastic gradient algorithm. All right, so one big challenge. Let me actually go back. One big challenge in the stochastic gradient algorithm is how to select the right batch size. All right, so that's B. Right, so lowercase b, that's the size of the mini batch size, and I already alluded. Sort of typical values are 1, 2, 4, 16, 32, 128. People sometimes go up to 1,000, but very rarely above 1,000. Right. So, but selecting the right mini batch size, it's a challenging and daunting task. Right. So clearly, you can do trial and error, and that's usually what people do. Right. So, but why is mini batch size so important? Right. So once you select your mini batch, all right, so that means essentially 32 subsamples, you then compute the gradients over those 32 samples. And you can compute those gradients in parallel. All right, so, and this implies that the larger is your batch size, you can then compute everything in parallel up to a certain limit, right? So because if you only have, let's say, 16 cores, even though this is usually done on GPUs. All right, so but let's just, for simplicity, let's talk about cores. If you have only 16 cores and you create a mini batch size of, say, 32, clearly you won't be able to exploit full parallelism, right? So you'd have to essentially do 2 sub batches of 16, all right? But the point is, if you have 16 or if you have 62, for example, mini batch size, you can there's the same amount of computational time involved if you have enough cores. All right. So from this perspective, you want to have large mini batch sizes. All right. So and here is a study from 2017. I'm listing it here. ResNet 50. That's a relatively large network. This is a deep neural network. So it's a CNN. All right. So if one selects a mini batch size of 256, then it takes 29 hours to train. But if one selects a mini batch size of 8,000, the training time goes down to 1 hour. All right. So now clearly, then the natural question here is, well, why not just having very large mini batch sizes? All right. So why not always go with 8,000 or maybe even larger, maybe even 15,000 mini batch size? All right. So maybe that 1 hour would go even further down. Well, so there's no such thing as free lunch. So if you have large mini batch size, you tend to find actually worse solutions, right? So, and this is intuitively, there's no science behind it. Even though sort of our work actually, we started with scientifically showing that the lower the mini batch size is, the better solution you would find, but we weren't quite able to show that, but we did a big step in that direction, right? And so let me try to intuitively explain why smaller batch sizes find better solutions, right? So first you have to keep in mind that in deep learning, we're talking about a non-convex optimization, right? So the loss function L, so this loss function L here, right? So this is heavily non-convex. Right, so it has a lot of local minima and a lot of local maxima. All right, so think about sort of a lot of valleys and peaks. All right, so and now what does it mean having a small batch size? All right, small batch size means that, go back here, right? So it means that there's essentially a lot of, so here you're selecting only small subsets. You are making very crude approximations to the full gradient, to the exact gradient, right? So that means that you are kind of jumping all over the place, right? So again, imagine sort of you have a surface that has a lot of valleys and peaks, and small mini batch size, it means you're jumping all over the surface, right? So, and as you jump all over, it's more likely that you're going to end up with a low valley. Right. So, but on the other hand, if your mini batch size is very large, you're not going to be jumping all over the place because you're going to be making very coarse approximations to your full gradients. So you will be kind of more committed to going to one direction, and thus you are less likely to find a good valley. All right. So you're more likely to go into a shallow valley. All right. So intuitively, at least sort of to me, intuitively. At least intuitively, it is expected that smaller batch size implies that you're more likely to end up with a good solution, and large batch sizes you're more likely to get, let's say, an okay solution. All right. So this clearly implies a trade-off in the mini batch in the mini batch size. So on the one hand, large mini batch sizes, low training time, but on the other hand, high mini batch sizes, worse quality solutions. All right. So and there's a big dilemma here in machine learning as to what is then the right batch size. Right. So you want to trade off these two aspects. All right. So what is and so this the implication at the bottom kind of implies what I have just said intuitively. All right. So if you have a smaller batch size, right, so you expect larger variance, right? So because again, if I go back here, right, so if you have 1 million terms and let's say the batch size, mini batch size is only 4, you're approximating 1 million terms with only 4 terms, right? So and as you select randomly those 4 terms, you're going to get a large variance, right? But if you select, say, I don't know, 900,000 terms, then the variance is going to be very low, right? So because those 900 terms are going to pretty accurately approximate 1 million terms. All right, so larger mini batch size implies lower variance. All right, so in other words, small batch size, large variance, and that implies worse stability, right? So meaning you're going to jump all over the place. This is what I explained earlier. So you're going to be exploring more possibility, and you're going to more likely end up with a lower training loss, and thus then that would then yield better predictions and generalization ability. All right, so I'm going to discuss this in computational experiments, prediction and generalization, right? But the main focus of this talk is essentially the first implication here: smaller batch size, larger variance. All right, so that's the part that I'm going to focus on in the last 20 or so minutes. All right, so the remaining first half of the presentation is going to be about this implication here: smaller batch size, larger variance. So we were able to scientifically prove this. And then the last portion is going to be about better prediction and generalization ability, and that's going to be a computational study. All right, so are there any questions at this point? So for the rest of the talk, keep in mind learning rates are fixed, right? So again, alpha t can be constant, or alpha t can be 1 over t or 1 over square root of t, or whatever. All right, so no more questions. All right, so then let me move on. All right, so variance, right? So we want to study variance of the gradient, right? So and of the loss function value as well, right? So there are two notions. So one is variance of the loss function value, and the other one is variance of the actual gradient. All right, so here is the variance. So I'm showing the variance of the loss function. All right, so by the definition of variance, variance is expectation of gradient. Sorry, this is the variance of the gradient. Sorry, this is the variance of the gradient equals to the expectation of the gradient square minus the square of the expectation, right? This is standard variance definition, right? So you should, but you all know this definition, all right? So as I said, intuitively, right? So intuitively, the variance should be larger if mini batch size is small, all right? So and we initially, so when we started working on this, we conjectured that this relationship should probably be 1 over b. All right, so but definitely intuition says that the variance should be inversely proportional to the b, or not inversely proportional, sorry, that it should be a decreasing function of b. All right, so when we postulated from the very beginning that it's most likely a function of 1 over b, right? So 1 over b is clearly a decreasing function. All right, so and we also postulated that it should depend on n squared. So n is the number of samples. And y of yn square, well, so that's because you have variance of, let's say, you have variance of n terms, right? So if you have a random variable, or let's think in this way. If you have a random variable that is a summation of 10 different random variables, then the variance of this random variable is, and this is very basic probability, is essentially it has 100 terms, right? So because the variance captures the pairwise interactions, right? So it should be, so if your random variables are from x1 to x10, x equals to x1 plus x2 up until x10, right? So then variance is going to involve, if you explicitly write down the formula, it's going to involve x1 times x2, x1 times x3, etc., right? So all pairs. And what's the number of pairs? Where it's actually in my example with 10, that's 100, right? So if you have n samples, then it's n squared. All right, so this is a conjecture, and we were able to show that it actually does depend on 1 over b, right? So, and that's the only dependency on b. So again, b is the mini batch size. All right, so why is this not? Why isn't it trivial to study the variance of the gradient? All right. Well, so you have to keep in mind that what is so you iterate, right? So let's say we are at a certain number of time steps, all right? So let's say, I don't know, 50 time steps, all right? So in other words, t equals 0, 1 up until 50, right? So it's easy to write the variance after step 1, all right? So that's easy. I mean, just a little bit of pretty much sort of basic probability, all right? So and that's the variance with respect to W1, right? So W1 is stochastic, right? So you just create just one single random mini batch, right? But now let's think about what happens in the next iteration, all right? So when t is 2, all right? So now W1 is already stochastic, and now W2 is even more stochastic, right? So because you sample your mini batch size twice, all right? So, and you can actually write W1 explicitly, all right? So, but writing W2 explicitly as a function of W0, that's very, very hard, all right? So, or actually, I should say it's not just very hard, but it's pretty much impossible, all right? So, and if you keep going, so if you get to 50, so at iteration 50, expressing W50 with respect to W0, all right? So, and all the mini batch sizes in between, so B1 up until B50, getting an explicit formula, it's pretty much impossible, all right? So closed formula is out of question, all right? So, and that's the reason why studying the variance, it's a challenging problem, all right? So because again, if there is a closed formula, then you use the expression for the variance, and voila, you're done. All right. So, but if you don't have an explicit formula, then it's unclear how to tackle this question. All right. So let me stress this fact again, because we had a little bit of a hard time persuading others of the significance of our work. Okay, because everybody thinks, well, you just do one gradient step, so you have a summation and variance of summations. Yeah, that's known, right? I mean, or that's easy to calculate. But no, that's just the variance in one single step of stochastic gradient, right? So, but we are interested here in the variance from the very beginning, right? So the variance in all 50 initial steps, samples, mini batch samples, all right, or 100 or 1,000 for that matter, all right. So, and that becomes now much more challenging to study, all right. So, so what we want, all right. So let's focus here only at the bottom statement here, idea, all right. So what we want is we want to study the variance of the gradient only with respect to W0, that's the first iterate, mini batch size, and then number of steps and learning rate, right? But as I said, learning rate, that's not the focus of this work, right? So learning rate is, my formulas later are not going to explicitly address the learning rate, all right? So they're going to focus mostly on B. All right. So and why also expectation? Well, expectation also because the variance expression here at the top of the slide indicates that in order to study variance, one should study expectation as well. All right. So again, our focus here is to study variance at iterate t as a function of W0 mini batch size B, the iterate, so the number of steps, and the learning rate. And again, the learning rate is less of a focus here. All right. So another kind of analogy that I want to bring here, or not analogy, okay, but more trying to persuade you that one step is different from n steps. For those of you that are familiar with a simple random walk, all right. So think about sort of you are in a grid, for example, and you make random steps on that grid, right? So that's what's known as random walk, right? So variance of one single step, it's very simple, right? So but variance after say 100 steps or 1,000 steps, that's a much more challenging problem, right? So what you see here in this figure shows the variance as you make more and more steps. All right, so here, okay, let's say when you make 100 steps, right, so you see that there's a huge variance, right? of the actual walks. All right, and getting computing or studying the variance after 100 steps, it's much more difficult than after just one single step. Right? So what are our main contributions here of the theoretical part? So the main contributions are that the variance is indeed a decreasing function of the learning rate, and it decreases roughly as a polynomial in 1 over b, right? So this is not now roughly, right? So it decreases as a function, as a polynomial in 1 over b, right? So that's our key contribution. And then the second contribution is it also provides sort of a tool to our work also provides a tool for calculating loss and variance from as a function of the initial point. All right, so these are two main contributions of our work. So our work is not about developing a new algorithm or anything like that. So it's basically the first bullet point here, decreasing property with respect to mini batch size. All right, so are there any questions at this point? None? All right, so let me now show you results. Okay, and this portion now it's mathematical, so I'll probably breeze through some parts, not going into details. Okay, but it's very technical, right? So and proofs here are very, very long. So you can find the paper on my webpage. So for those of you that are interested in the proofs are very technical and very very long, right? So how are we going to tackle this? So one idea is, all right, so first, because we want to study this, we want to study variance and everything, so gradients and iterates as a function, as functions of mini batch size b, right? So we're going to add a superscript b to indicate that each value depends on b, right? So, and that we want to study it with respect to b. All right, so as is usual in such problems, you want to do induction on t. All right, so we want to get some kind of a recursive relationship between variance after t steps. Okay, sorry. We want to express variance after t minus 1 steps as a function of the variance after t steps. All right, so that's standard sort of inductive argument. All right, but here we actually have two quantities. So we have the actual iterates that are stochastic and the underlying gradients that are stochastic. All right, and in this work, sort of we actually establish a recursive relationship between WT plus 1 and gradient, and then from the variance of the gradient, and then the variance of the gradient, we transition over to the variance of the iterate, and then back to variance of the gradient, etc., etc. Right? So in other words, we need to study variance of the iterates, right? So or trainable weights W, and variance of gradients G. Right? So and then we follow this kind of path in order to get it down to the as a function of W0B. All right. So that's kind of the line of attack. But actually, the key idea is somewhere else. All right. So let's first focus on linear regression. All right. So we have two lines of results. So one results are for linear regression, and the other results are for deep neural networks. Right. So let's start with linear regression. All right. So this is the linear regression loss function. All right. So we have n terms, standard mean square error loss function. All right. So and in the stochastic gradient setting, you select the mini batch size BTB. Right. So then you calculate the approximate gradient. That's at the bottom. Right. So GTB is just a summation of the gradients over samples in B. Right? What are those gradients? Well, that's it's easy, right? I mean, it's easy to calculate the gradients here because all you have to do is you take the derivative of this square function. That's easy, so you can explicitly write down the gradients. All right, so and that implies then you can also explicitly write down the norm of the gradient, the one-step variance of the gradient. All right, so norm of the gradient. So this is the top expression here. Right. So forget about this filtration here stuff. This is just mathematical technical detail. All right. So all right. So to derive what is on this slide here, it's pretty fundamental mathematics. Right. So no deep mathematics. Right. So just write G. Right. So whoops. All right. So just essentially. Use this formula here, so how the iterates are upgraded, the definition of the mini bed size gradient, and then calculate explicitly the gradient. All right, so replace this form here with a derivative of this expression here over only a summation subset. All right, and then use the out of the box variance formula. All right, so nothing really fancy here. You're going to get this expression here at the bottom. All right, and this expression now has two terms. All right, so you see the first term and the second term. Right, so and furthermore now, if you expand the middle term, so this one over here. All right, so if you write the norm as the inner product, all right, so you get this expression at the bottom of the slide. All right, now that's very important actually. All right, so why is this important? Well, it's important because we see here gradient terms. All right, so we see here essentially, okay, so the first term here is at iterate, is at time t, right? So we started at time t plus 1. Recall that we want to do inductive proofs, right? So we start with t plus 1, and we were able to express it as a function of t, right? So that's the first term, right? So we're happy with the first term, right? So the first term says, okay, we'll be able to do recursion, right? Now the second term, well, that one is already tricky, all right? So because it's unclear really how to imply inductive step here, because we don't directly have norm of L here, right? So we have some inner product. So this bracket here that represents the inner product, right? So we have some inner product and some xk transpose, right? So that the second term already it's unclear how to apply induction here, but it's even less clear for the third term, right? The third term now it has GTB, all right? So which is great. Right, so we have reduced t, but it's multiplied by some matrix, right? So, but we started with just norm of the gradient at t plus 1. All right. So if you want to apply straight induction, it's impossible because here, right? So we started with GT plus 1 norm square, but in the recursive definition, we don't end up with just norm GTB square. We end up with norm xk transpose GTB. All right, so this actually prevents us to do induction out of the box. Right, so I hope you all see the difficulty, right? The challenge here. You cannot, with this kind of approach, there's no way to carry out induction. Right, so the key idea that Shin came up with is that instead of making a recursive statement for just norm of the gradient, we're going to make it for a matrix times norm of the gradient, because this representation here at the bottom, the last term on the slide, is also a matrix times norm of the gradient. All right, so now if we start with a matrix, and if we can show that this last term here, it's again going to be a matrix, not necessarily the same matrix, right? So but a different matrix, then we should be able to carry out induction. All right, so here I'm only highlighting that the difficulty is in these terms xk transpose, right? So in other words, that the gradient gets multiplied by a matrix. All right, so what we do is here the bottom line here now outlines the key idea. All right, so instead of studying the expectation of the norm of the gradient, we're going to study expectation of the norm of some matrix A, any constant matrix A, times gradient square. All right, and we're going to do the same then for the gradient of the of individual samples. All right, so we're not just going to study the gradient of the individual samples, but A times, so general matrix A times gradients of individual samples. All right, so this is the key idea here, right? So in other words, we are going to show a more general result, right? So and by showing a more general result, or by studying the more general result, we'll be able to actually apply induction. All right, so this is kind of make it more complicated so that you can carry out the inductive step. All right. Okay, so now I'm going to be skipping this sort of lemmas. All right, so this is just so now that we have we agreed, or hopefully I persuaded you that we want to study a more general result, or we need to study a more general setting. Right. So now first, what is the one step variance? All right. So hopefully I made an argument before that if you don't have A here, or if A is identity, then standard probability. All right. So now we need to generalize that standard kind of probability result because we have general matrix A, but it's not that hard. All right. So this is what is shown here. So are there any questions at this point, by the way? Okay, so let me go back to this slide. Are there any questions at this point? None? All right, so let me continue. All right, so we then end up, so in order to carry out induction, so I'm going to just, you better you better listen to me rather than watching this pretty ugly expressions here, right? So it turns out that if you really want to carry out induction, it does not suffice to have just one single matrix A, all right? So, but you have to deal with actually several matrices A, and they're all constant matrices, all right? So, and you want to get actually a more general result where A from the previous slide is actually a summation of all this AI matrices times your sample. So Xi's are samples here, by the way. I should have said it earlier. Right, so Xi's are samples, right? So you want to you want to have the A to be a form of this form here, where you have several AI matrices. All right, so, and then you you do some calculations to calculate the variance of this expression here, and you end up with this formula here, right? So, the important part here is you start with this much more general form, right? So where you have many constant matrices AI at time t+1, and then you can express this as a function of quantities that involve only time t, right? So left-hand side is a function of t+1, has t+1. Right-hand side has only a function of t, right? Now the matrices are different, right? So the matrices on the left-hand side, there are some matrices AI. The matrices on the right-hand side, there are some different matrices BI, all right? But BIs, they don't depend on our weights W's, all right? So they're constant matrices, right? So and you have their expressions, you have them at the bottom, all right? So they're constant matrices. All right, so this alludes to the fact that we might be able to do recursion, right? So because we started t+1, we end up with t, or we rewrote it as a function of t that has very similar form, right? So it's a summation of some matrices. All right, so that's very promising, and indeed, sort of this actually can be carried out. All right. So the induction step then can be carried out. All right. So now so there's a relatively kind of long proof here. So you can use this observation here to then inductively show that, or by using induction, then one can show that the expectation of the summation of some constant matrices times gradients is a decreasing function of B. All right, so this is in the linear regression case. This is our first result. All right, and then so similar results, then we can get the variance of some arbitrary matrix B times gradient that's a function that's also a decreasing function of mini bed size B. Right. So for any square matrix B. All right. So the linear regression case now is done. All right. So we showed what we wanted to show, right? So it's a decreasing function of B, the variance, right? So and we actually show a much more general result, right? So because we are only interested in capital B being identity, right? So but we had to introduce this capital B in order to carry out induction. All right. So any questions at this point? The rest is now deep learning networks. Are there any questions? None. All right. So the goal next is to generalize this to deep learning. To deep neural networks. All right. So and we were able to do it, but not really for any neural network. Right. So we were able to do it for linear neural networks. So those linear neural networks are neural networks. They're deep neural networks, but without activations, right? So, or in other words, activations is identity. All right. So for such a network is FW. All right. So it essentially W consists of W is a set of trainable parameters, and it consists of matrices WL if you have L layers, WL, WL minus 1 down to W1. All right. So these are all matrices, right? So essentially here W. You see here the expression. W consists of matrices W1 up until WL. All right, so and these are called deep linear networks. Right, so and again, the only difference between deep linear networks and general deep networks is that we are not assuming activations. Right, so activation is 1. Right, but the point is that this, even though it's called linear, it's actually not a linear function, right? Because it's a multiplication of several matrices, right? So it's not linear, and thus it's not convex and anything like that, right? So there can be biases, okay, but we leave them in for ease of notation, right? All right, so any questions about deep linear networks? All right, so we want to get similar results for the variance of gradients as the decreasing functions of B for deep linear networks. We were not able to get exactly the same strong result, but we were getting sort of pretty similar results. Because that's what I'm going to present next. All right, so and I'm not going to go into details here, right? All right, so let me skip that. All right, so we have our loss function. So first of all, with deep linear networks, we were not able to show the result for empirical loss, which means loss is the summation of oversamples. All right, so we had difficulties there. We were not able to tackle that. All right, so but we changed that into so-called population loss. All right, so that's the expectation over normal distributions of the loss function. All right, so empirical loss, right? So empirical loss is the case where you have a finite number of samples from population loss, which is normal, 0, and 1 over an identity. All right, so we are not able to study empirical loss, but we are able to study population loss. All right, so now the first thing is what is the gradient of this thing here? All right, so and it's actually not that clear what is the gradient because bear in mind these are matrices, right? So it's kind of it's gradient with respect to matrices, even though it is really gradient with respect to individual entries in the matrices, right? So but how do you express the actual derivatives with respect to matrices? They're known results, okay, so but they're not that straightforward, right? So here you have expressions for the gradients, right? So I'm not gonna it's not that important what are the expressions. All right, so these are not our results, all right, so these are known gradient expressions. All right, so you have them here at the bottom of the slide. All right, so now in the regression case, we said we had to generalize the result, right? So the statement, the conjecture, right? So by studying matrix A times gradients, right? So for deep neural networks now, we have several matrices, right? So that means in terms of trainable parameters, right? So that means that probably we need to generalize, we need to complicate things further, not just having just one single matrix. Right, so and indeed, sort of, we have to introduce this notion of multiplication terms. Right, so if we have a set of parameter matrices, right, so these are essentially, they correspond to our W matrices, right? So in constant matrices, right, so these are going to correspond to samples, or so some expression of samples, right? So we have a bunch of matrices, parameter matrices corresponding to trainable weights, and constant matrices. Right, so the multiplication term is any product of these matrices and their transposes. All right, so here's an example. All right, so here at the bottom. All right, so if you have x1 and x2 and c1, c2 constant matrices, for example, the expression x1 times x2 times x1 times x1 transpose times c1 times x1, that's a multiplication term. All right, so and so is C1 x1, C2 x2, for example. All right, so just take any products of the matrices and their transposes, and that's a multiplication term. All right, so now, all right, so let's forget about that. All right, so we're going to use law of iterated expectations. All right, so and that's a technical detail. All right, so I'm gonna skip this. That's how all right, so let me skip this. Okay, so I go to one of the lemmas. All right, yeah, and here's now where notation gets ugly and proofs are also very ugly. All right, so so we had those. Sorry. All right. So we have parameter matrices and constant matrices. Right. So parameter matrices, that they correspond to W matrices. Right. So which are our trainable matrices, and constant matrices, they correspond to matrices of the nature xi transpose. Xi's are samples. All right. So and then we also have optimal matrices, W stars. So they are mentioned on previous slides. I didn't talk about them. We also have optimal matrices, W stars. Those are also treated as constant matrices, right? So I go back here. Well, actually, okay. So I can, yeah. So I think this is actually good. All right. So the parameter matrices are essentially xi's times xi transpose, and constant matrices are optimal trainable matrices and trainable matrices. All right, so that's the setting that works in order to come up with proofs. All right, and so okay, so we were able, first of all, we had to come up with an expression that expresses the expectation of a bunch of constant matrices times normal. Vectors that come from normal distribution times fixed matrices. Right. So this expression here. Right. So one can ask, well, isn't there a closed form expression for this? No, it's not. Actually, there isn't. Right. Even though you have normal distributions, all right, so writing this expectation here in a closed form, it's impossible. All right, so we have this, but we were able to get some kind of a closed form, even though we are not really explicitly stating what are the M matrices. F here, yeah. So those, okay. So these are the aspects that I didn't that I brushed off. So those are filtrations, all right. So strictly speaking, mathematically, they're called filtrations. Essentially, they capture history. All right. So F0, it means the very first iterate. All right. and ft, it means history up until time t. All right, so there's like so you can distribute the slides. So formal definition of FTs are somewhere on early slides. Okay. All right, so again, FT is history with respect to or everything up until time t. All right, so and this means conditioning, right? Conditioning on everything that happens up until time t. All right, so law of iterated expectation. So that's a known probability concept. All right, so let me actually go here, right? So we have a bunch of lemmas now that go that recursively express WT plus 1 with respect to gradients, and then gradients with respect to weights with respect to gradients at the previous iteration, etc., etc. And this relationship here are of this kind of ugly form that you see here, all right? So that you see in this slides here. All right, so so to show all these lemmas, sort of, it's very, very technical. All right, so and again, I want to emphasize again that we have to show a much more general result and not just the straight variance. All right, so we're taking again matrices, so summation of matrices multiplied by gradients. All right, so what are the main results now? All right, so let me skip that. All right, so here, all right. So what are the main results? What's the main result? Okay, so if we take any multiplication term that involves parameter matrices, right, which are or our trainable matrices, right? Sorry, trainable matrices, right? So take any multiplicative term that involves parameter matrices, right? So let's calculate the expectation of that term. All right, so let me again sort of try to better explain what am I talking about, all right? So all right, so let's replace here x's with trainable matrices and c's with any constant matrices. All right, so the result there, the result in the theorem says the expectation of this product here then is whatever it's stated in the result, right? So we are interested only when all these x's essentially are identities, and we have just ci c1 to be one parameter, right? So but that doesn't allow us to carry out induction. So we have to complicate it by studying expressions where we have a bunch of constant matrices, multiplications of a bunch of constant matrices and their transposes, and a bunch of parameters and their transpose of the actual parameters. All right, so the result here says that if you take any multiplicative term that involves our trainable matrices, all right, so then the expectation is a polynomial in 1 over b. All right, so this is a very important result. All right, and then we have a similar result now that says, or this is kind of, it follows from the result that I have just showed you. Okay, by taking a bunch of matrices being identity. All right, so we have that the variance of the gradient is a polynomial in 1 over b. All right, so again, the variance of the gradient at step t, right, so is a polynomial in b. All right, so again, b is the mini-batch size. All right, now this doesn't actually show the decreasing property, right? So because in the linear regression case, we actually were able to show the decreasing property, right? So because we're not saying, we cannot show that the beta coefficients are all positive, because if they're all positive, then the entire right-hand side here would be decreasing, right? So we cannot show that, right? But we can show that if the mini bet size is larger than some quantity, then this polynomial here is indeed a decreasing function of B. Right. So again, we were able to show that for mini bet size larger than something, the variance is actually a decreasing function of B. All right. So and numerical experiments have actually showed that this B naught is actually very small. It can be as small as 1. Okay, which essentially means that computational experiments actually show that this polynomial here is a decreasing function. All right. So, but that's numerical observation, not a scientific one. All right, so that's enough of theory, right? So these two are our main results. Together with the linear regression result, these two are our main results. All right, so some experimental results. All right, so, and here I'm only going to show you essentially so kind of validating some of the results, and also showing that the results hold also for nonlinear deep neural networks, right? So those that have activations, right? So here you see, so we as number of iterations. So the x-axis is the number of iterations, and the y-axis is the log of the variance, and then the different series here are with respect to different mini bet sizes. All right, so and you see that so the smaller the bet size, right? So our results say that smaller bet size means larger variance. All right, so and indeed green is bet size of 4, and then if you go down, purple is 16, and then 64 and 256. You see that the curves actually nicely stack up, right? So so this is just numerical, essentially, confirmation of our result, because these are actually linear deep nets. All right, so our results directly apply in this case here. Let's not worry about the right chart here. All right, so and then we also created some synthetic data sets that also we observed the same. All right, so we try to kind of come up with data sets where it's less intuitive that they're decreasing functions of B, and they turn out to be decreasing functions of B. All right, so let me just breeze through this. All right, so here are some more interesting experiments. So they relate to the MNIST data set, and here we use actually a CNN. All right, so our results now no longer apply here because there is a nonlinear activation function. All right, but computational experiments show that the results actually hold here as well. Right, so and actually I shouldn't say results; there will be more conjectures. Right, so because we cannot show them. Right, so here you have mini bet size, so log of the variance, mini bet size of 64, that's purple, mini bet size of 128, that's, what is this, orange, brownish. So, and you see that orange brown is always below purple, right? So variance is lower at every epoch. All right, so this is, so the other one is about generalization. All right, so I said that at the very beginning of the talk, I said that small bet size leads better generalization. All right, so the y-axis here is essentially generalization, which is gap of accuracy. And you see that purple, which is 64, it's lower, right? So meaning gap of accuracy, which means generalizes better than the orange, than the yellow one, which is bet size of 128, then the orange one, which is bet size of 256. All right. So the right chart confirms that small bet size generalizes better. All right. So and then, all right. So let me skip this. I want to go. Yeah. So I showed you fully connected network. That was the first experiment. I showed you MNIST and CNN. All right. So it kind of works. Not kind of. The conjectures sort of hold for CNNs. And lastly, we tried also transformers, all right? Or in other words, recurrent neural networks. So here we took XLNet, which is one of the transformer model and the famous or widely used, let's say, Yelp data set, right? So, and again, so we tried only two mini bed sizes. So here training is very expensive. So we tried only 32 and 64. And again, sort of variance is smaller for lower mini bed size. And then generalization property also holds in the same observation from MNIST holds here as well. All right. So in other words, we confirm, even though we don't have scientific proofs, all right? So we confirm by means of this transformer on the Yelp data set that lower bed size implies higher variance, and it implies better generalization. All right, so some of the references, and that's it. I said 1 hour. All right, yeah, so it was 1 hour. Okay, so thank you very much. So again, it was a pleasure sort of giving a talk.